In this pure theory section, I will be discussing key findings related to liquid clustering. You can find more details on my GitHub page. The link is available in the description below. Let us start by understanding what liquid clustering is about. Liquid clustering is an optimization technique that was introduced by Databricks on Delta Lake tables. Liquid clustering logically cluster your data by values in one or more column, all without basically changing the physical layout. This feature is available in Data Lake 3.1.0 and above. Under the hood, liquid clustering groups together rows with similar values in the clustering column. This grouping happens during the write operation. All the grouped rows end up stored in the same files or a group of files. So when you run the queries on the Delta um, table, the Spark can easily skip all the unrelated files by consulting the file level static information. Now let us compare liquid clustering with other optimization technique that is available in Delta Lake, like high partitioning or high style partitioning or Z-ordering. Let us understand this with a sample data set. The dataset here captures the transactional information. When you do a high style partitioning on a large dataset, the data here is organized into directory based partitions, one directory per unique combination of month and country. As shown in the figure, the high style partition could lead to imbalanced partition size. Some partition end up with very few records, resulting in many small files. Others grow disproportionately large, making them inefficient to process. This uneven distribution creates problems such as data skew, slow query performance. This is a key limitation of static partitioning, where it cannot handle evolving data volumes or high cardinality fields. Now moving to the Z-ordering. Like liquid clustering, the Z-ordering also cluster the data within or across the file to improve the query performance. The Z-ordering is applied on a high cardinality columns like center ID. Usually the Z-ordering is applied in combination with the partitioning so that it basically enhances the data skipping. In Z-ordering, a C cube is a group of clustered files that meets a specific size threshold. Once this threshold is reached, the C cube is considered stable and is excluded from the future clustering operation. Now let us understand the data layout for the given sample dataset, where we apply partitioning by month and clustering by sender ID. In this layout, each partition is created based on the month, and within each partition data is clustered by a sender ID. From the figure, the problem here is the clustering happens only within each partition, which means there is no organization of data across the entire data set. From the diagram, we can see that the Poland, Mexico and Germany all are having very small uh, size data. If that could be reorganized into a single file, that would have lead to a better performance. So that's why that's why we say that the clustering happens only within each partition. Another limitation of C ordering is the change in query pattern, or applying a Z order again is a compute intensive process, and the entire C ordering process is not increment, which means whenever a new data is inserted, if you have an unstable Z cube, entire file associated with that unstable C cube will be clustered again. All these drawback can be avoided with using liquid clustering. Now coming to liquid clustering, it adapts to the clustering based on the query pattern without constraining the cardinality of the columns. Also remove the need for static partition and can dynamically merge or further divide the files in order to arrive at a balanced data set. In liquid clustering, the clustering itself is an incremental operation. Here, it only processes newly ingested data. It allows cluster on write, or sometimes it is referred to as eager clustering. Means clustering is part of the ingestion process. As you can see from the figure that liquid clustering was able to combine files of Poland, Mexico, and Germany into a single compact file. This may not be possible with C ordering, as C ordering works only at the partition level, not across the partition. That's all regarding the comparison. Now let's move on to the implementation details. To use liquid clustering, it should be defined at the creation of the table, or it can be using an alter statement. So we need to use the phrase cluster by and mention the columns by which you want to cluster. Once after creating the table, there is a need for you to trigger um, uh, optimized job to run optimized job to trigger liquid clustering. Now the question is, can liquid clustering both and can be applied with partitioning? Yes, it can be applied with partitioning. Like we have seen, you can partition based on some sort of a low cardinality column, and then you can apply liquid clustering um, on the columns by which the query pattern is on the column which the query patterns filter conditions are. Below table describe when to use liquid clustering for a delta table over a partitioning. Fabric underline use delta tables. So the liquid clustering is available on the fabric tables. So the creation of the delta table with liquid clustering is similar to what we have seen before. And like I mentioned earlier, there is a need for you to run an optimize command to basically trigger the clustering process. Coming to the challenges associated with liquid clustering, with the increase in volume of data for a company, the need for analytics also keeps growing. The first challenge would be, with so many tables around it, it is tough to figure out which one actually needs a clustering. Then even if you pick a table, it is not always clear which columns to cluster on. On top of that, the business team keeps changing how they query the data. So what worked before might not work later. To solve these problems, a data engineer often needs to connect with downstream users to understand how the data is being used. From all these challenges, it is clear that we need an automated way to manage the liquid clustering. This is where the automatic liquid clustering comes into the picture. Databricks introduced automatic liquid clustering as a part of DBR 15.4, and it is expected to be available in all the later versions. With this feature, the Databricks automatically handles all the data layout decision for you, so you don't need to worry about tuning it manually. To enable this feature, you need to do two things. First, you have to enable the performance optimization for your DBR. Second, um, you have to create the table using cluster by auto class. Remember, these are only applicable to the Unity catalog managed tables. So once this auto liquid clustering is enabled, Databricks in the background performs three things. It's a continuous process. Okay, so the first step is it basically collects the telemetry data associated with the table. By these elementary data are analyzed are the query scan stats, such as query predicates and join filters. Basically, this help to determine whether a table would be benefited from either introducing a clustering key or evolving the existing clustering key. The second process is it models a workload to identify the eligible columns that would serve as a clustering key. So the final step is once these potential keys are identified. So this is a cost-based model because the performance improvement are evaluated against the cost of introducing the clustering keys. So that's it regarding the liquid clustering. And before we close, one more thing, this automatic liquid clustering is only available on DBR. It's not there in Fabric. So that's it. Thank you.